So in order to understand ionization energy, we're going to do this little example to help us understand it. So find sodium on the periodic table. How many valence electrons does sodium have? Okay, 1. And how many total valence electrons does sodium want to have a full shell? 8. So it needs to get to 8. So is it easier for sodium to lose 1 and drop down in energy level or gain 7? Lose 1, okay? So sodium, it's much easier to lose 1 electron. So now find fluorine. How many valence electrons does fluorine have? 7. Okay. And how many does it want to have a full shell? Okay. So is it easier to gain 1 or lose 7? Okay. Okay, so is everyone with me so far with this idea? Okay, so keep this in mind. So now, which element do you think is easier to steal an electron from? Sodium or fluorine? Okay, I'm going to go back, and then we'll come back to this one. So then, with that being said, which one's going to be easier? Sodium, okay. It only has 1 valence electron. It wants to give that up, so it drops down to a full energy shell. Okay. So that idea right there is what ionization energy is. Okay. So ionization energy, I'm going to underline if we want to shorten this. It's the energy required to remove 1 electron. Okay. Technically from like a neutral gaseous atom of an element. Okay. But if you really want to like condense this to really what's the important stuff, so it's just the energy required to remove an electron. Okay. And so there are some atoms out there like sodium that easily want to give up an electron and it doesn't take very much energy. And then there's other atoms out there like fluorine that almost have a filled valence shell and are basically never going to give up an electron. Okay. And then in your notes, I do want you to draw the trend for this. So where I have the periodic table, you could just draw a rectangle. You kind of with me here? So instead of drawing the periodic table, just draw a rectangle. Okay. And so the trend for increasing ionization energy, it increases as you go up a column and as you move to the right. If you would like to condense that, you can also just draw a diagonal arrow showing that it increases up and to the right. And then off to the right, these are actual measurements for some of the elements. So just showing how many kilojoules of energy are needed for every 1 mole. Okay. So if you look here, like sodium only needs 496 kilojoules of energy to take an electron. Okay. And then notice, I think we did fluorine in our example. Fluorine needs 1,682 kilojoules of energy to take an electron. Okay. So this first column, they're low numbers because they only have 1 valence electron. So do they want to give those up? Right. They don't want them. So these ones are relatively low. Let's jump all the way over to noble gases, though. Okay, so noble gases, they already have a filled valence shell. Are they going to want to lose an electron? No way. Okay, so look at these numbers. Are these all really high numbers? Yeah. Okay, so it would take a lot of energy to take an electron from a noble gas. But let's look, why does it take a lot more energy, double, to take it from helium from xenon? Right? Are they both filled shells? Yeah. Both filled, but helium takes twice the amount of energy. Helium has 2 valence electrons, which is all helium can have, so it's a filled shell. Except, what do we know about the size of helium? Is it big or little?
It's tiny, boy.
Tiny. What's the charge of the nucleus? Positive, negative, or neutral?
Neutral?
What's inside the nucleus? Nope. Protons and neutrons. What kind of charge do protons have?
Positive.
Positive. Okay. So positive nucleus. And what kind of charge do electrons have? Negative. What do opposite charges do? And they attract them, right? So helium is this tiny little atom. Its electrons are very close to the nucleus. And what do positives and negatives do? They attract, okay? So these electrons are held very tightly in. It takes a lot of energy. If we go down here to xenon, xenon's much bigger. So that nucleus is much further away from those electrons. So is that attraction going to be stronger or weaker than helium that's right here? Weaker, right? It's further apart. It's a weaker attraction, which is why it's a little bit easier. Does that make sense, like the big difference there?
Kind of. That was a little bit confusing for my brain.
Okay. What you need to know is this right here. Okay, you need to know it increases up to the right. Okay, there is such thing as like second ionization energy, third ionization energy, fourth, and so on. Second is just, if we've already removed one electron, how much energy does it take to remove the next electron? Okay. Third would be how much energy does it take to remove the electron after that. In this class, we'll only look at first ionization energy. Yeah. Okay, next is atomic size. In our activity, we called it atomic radius. Is radius and size going to be the same thing? Okay. This one, I didn't do a definition. I feel like we know. But you do need to know the trend. So in your notes, instead of the periodic table, if I were you, just draw a rectangle. Okay. And then the trend for atoms increases to the left and down. Or if you want to draw the diagonal, you can draw the diagonal. And then over here, this is a picture representative of what we should have gotten on our little activity today. So we can see as they move to the left, they get bigger, and as they move down, they get bigger. All right, so then we're going to compare those two characteristics. So ionization energy and atomic size. As atoms get larger, do you think it gets easier or harder to remove that outermost electron? Okay, so as a table, talk to the people you're sitting by. Okay, so little atoms, is it easy to steal electrons from, or big atoms, is it easy to steal electrons from? Okay, so discuss it, then we'll go over it. Okay, I'm going to use some magnets to just kind of help with that demo. So what's in the nucleus of the atom? Protons, what kind of charge do they have? Okay, pretend this is our nucleus. Positive. Electrons are moving around over here, what kind of charge do they have? Okay, what do positive and negative charges do? Okay, attract. So if the atom's small, the electrons in the nucleus are close, yes? Okay, how strong is that attraction?
Really strong.
Okay, so like if I let go, what happens? Like it's strong enough that it's gonna like pull it, right? So like this attraction is strong. If the atom's big, where are the electrons? Farther out. What is this attraction? If I drop this, where's it gonna go? Yeah, so it's weaker, right? It's a weaker, if I drop this here, it's a strong enough attraction. If I drop it here, what's going to happen? Okay, so which one's going to be easier to take an electron? From here or way out here?
Way out there.
Way out here. Okay, so bigger atoms, it's easier to take that electron because the attraction's weaker. Okay, just like this magnet. Okay, our last like characteristic or trend we're going to look at is something called electronegativity. If you would like to shorten it, just call it electron greediness. And then I'm going to explain what it is. But I think instead of writing like the long formal definition, write down electron greediness in your notes. And so what that actually means is when two atoms are bonding together, which atom has the greater ability to pull electrons towards it? Okay. So a better way to think about that is the game of tug of war. Okay. So picture tug of war in your head. And then instead of two humans playing tug of war, picture two atoms. Okay. So the more electronegative atom is going to win the game of tug of war. Okay. So they're going to pull, and instead of a rope, it's going to be electrons. Okay. So the more electronegative, the more you're going to pull electrons towards you. So again, think tug of war to rope. The less electronegative, you're going to lose that game of tug of war. Or the electrons are going to go from you to the other atom. Okay. So again, in your notes, I think electron greediness is good. And then if you need like a little memory reminder, I'd even write like think tug of war. Okay. And so our trend for electronegativity increases as we go up and to the right. And remember, if you don't want to draw like the periodic table, you can just draw the rectangle. And you can either draw your arrows going up and over to the right, or you can combine these and do one big diagonal arrow. So whichever one you know you want, but you just need to know it increases as we go up and to the right. So how we quantify electronegativity is we have these arbitrary units on something called the Pauling scale. What does arbitrary mean?
What's a word?
It's a word. It's like it's man-made. So it is like this made-up unit. There's no way to actually measure electronegativity. Okay, like there's no measurement like utensil. Scientists have just like assigned numbers to these elements just to somehow quantify it. Does that make sense? So we don't measure it, but we just need a way to quantify it. So when we look at electronegativity values, noble gases are omitted. Why do you think that is? What's special about noble gases? What's special about their valence electrons?
They already have all that they need.
Good. Okay. So noble gases, they already have a filled valence shell, so are they going to want to bond? Okay, they don't bond. Can you play tug of war all by yourself?
If you wanted to.
No, like you literally could not, right? So noble gases don't have electronegativities because they do not bond. Electronegativity is solely when you're bonding who's sealing the electrons. So if you don't bond, do you have an electronegativity? No. Okay, so no noble gases. And then here's just some of the units. So cesium, we call it the least electronegative element, and it's given this value of 0.7. Fluorine is the most electronegative. It has a value of 4. All the other elements are in between. And then take a look at the periodic table. Find cesium. It's at the bottom left. Okay. Which one is even lower than cesium? Okay, francium. They've omitted francium. It breaks down every 22 minutes. Okay, so like francium is not stable enough to really count, but like I don't want you to be confused why we're saying cesium instead of francium. Okay, so now let's compare how's electronegativity and ionization energy similar, and like how are they having the same trend? Okay, so let's pick on fluorine to help us understand this. So fluorine is over here. Okay, so fluorine has a really high ionization energy, which means it's really hard to steal one of fluorine's electrons. Okay, so let's think about this. How many valence electrons does fluorine have? 7. Okay, and how many does fluorine want to have? 8. So is fluorine really, really, really close to having a filled shell? Okay, so is fluorine going to give up any electrons and get further away from having a filled shell? No way. Okay, it takes a lot of energy to steal an electron from fluorine because it does almost have that filled shell. Okay, on that same note, if we look at electronegativity, fluorine has 7, and how many does it want?
1.
One more. One's 8, so it needs one more. Okay, so if fluorine bonds, what's it going to do to another atom's electrons? It's going to steal it, okay? Fluorine takes an electron from anything, okay? So it steals any atom's electrons so it can get to 8. Okay. Let's go pick on cesium now. So cesium is down here. Cesium has a really low ionization energy, meaning it's really easy to take an electron from cesium, okay? So how many valence electrons does cesium have? Just 1. And how many does it want to have? 8. So is it easier for it to lose 1 or gain 7? Lose 1, right? So cesium's over here. It wants to lose an electron. Okay, so it gives an electron up super easily. So when cesium bonds, does it want any more electrons, or is it trying to get rid of electrons? It's trying to get rid. So like it's not going to pull any electrons near it. It's trying to get rid of its own electron. Okay. So does it make sense why these two are the same trend? Okay, so then the last thing we're going to look at is if we use the periodic table, well, how do we know which elements are either like higher or lower in these trends? Okay, so the first one we'll look at is electronegativity. If you don't have your periodic table out yet, go ahead and get it out. Or you can just look at the large one on the wall. Okay. So first, it's good just to know the trends. Like with your hand, show me like the direction of the arrow for electronegativity. Which way does it slope? Okay. So when I work on paper, I'm just going to draw it, right? So it increases as we go up and to the right. Okay. So then if we look at the periodic table, which element is furthest up and to the right? With what exception? Okay, no noble gases, right? So besides the last column, which element is furthest to that top right? Okay, so the most electronegative is fluorine. Okay. And then which one's the least? So which one's closest to the bottom left? Okay, we can do francium. If you wrote cesium because francium is so unstable, it's perfectly fine. Okay. All right, next we're going to look at radius. Again, with your hand, show me what direction does the arrow go for radius.
She saw.
So radius should go down and to the left. Okay. So then, which atom is furthest to the bottom left? Okay, francium, right? It's all the way over at the bottom left. Okay. So then the smallest one is all the way over at the top right. So which element is top right? This time noble gases count.
Helium.
Helium.
Hydrogen is the exception.
Yes. All right. Ionization energy, show me with just your hand. What's the direction of the arrow? Okay. All right. So increase as we go up and to the right. So highest ionization energy, which element's all the way up and to the right? Okay, helium. And then lowest, which one's all the way down to the bottom left? Okay, francium. Okay, we're going to do just one more practice problem of each of the trends. Okay, so now we're going to look at multiple elements together. All we're going to do is take these 4 elements and just rank them by increasing ionization energy. Okay. So first, what does increasing mean? Getting bigger, okay? Low to high or small to large. All right, so when we do these problems, you're going to do these on your own without me when I'm done here. So first, I just recommend draw the arrow on paper. So what does the arrow look like for ionization energy?
Down.
Up. It's okay. Okay, up and to the right. So like when you do these on your own, draw the arrow. Okay. Could you break apart the diagonal arrow if you want to? Sure. This is the same thing as up and over. Okay. So however it like makes more sense in your head is fine. So now if we want increasing, we want smallest to largest. So you're going to look at these 4 elements. Of these 4, which one is the most like bottom left? Okay. So RB or rubidium is furthest to the bottom left. Then which one comes next, closest to the bottom left? Which one? Okay, potassium. Then which one? Phosphorus, and then chlorine. Okay, does that make sense? So we're just going to draw the line, and then we're just going to kind of think it through if it's... All right, so now we're going to do the same thing with electronegativity. So again, draw the arrow for electronegativity, so it increases as we go up and to the right. And then we just look at which element is furthest on the bottom left. So we have rubidium, then potassium, then phosphorus, then chlorine. And then finally, we're going to rank the following elements by increasing atomic radius. So again, start by drawing your arrow. So atomic radius increases as you go to the left and down. So this time we're going to start the atoms that are in the top right and work our way to bottom left. So of these 4 listed, chlorine is the most top right. Then phosphorus, then potassium, then rubidium.